Good morning, everybody. This is Radiocrafts calling in with a webinar on understanding range. Now we are a couple of minutes, according to my watch, over 10. So we will, or actually it's just about 10. So we will start now, and hopefully the last one will join during the introduction. So this webinar today is about understanding the RF range and what influencing factors there are and how you can optimize the network for range. This will be held by me, who is Ørjan Nottveit. I'm the R&D Director at Radiocrafts. It was also supposed to be co-edited by, co-hosted by Omar Khalil, our application engineer, but unfortunately he was sick today, so it will be only me for this webinar. Hopefully, I will be able to teach you something still. So the discussion points of this agenda is understanding range. That means, why don't I get the range I anticipate? Is often the question we get from the customers. What factors influences the range? What tips and tricks can we do to increase the RF range? And then we will finish off with a case study of one of our newer modules where we actually did quite a few of range tests. So hopefully this will give you a better understanding of range and the factors and a general understanding of the range we have on our products. So the first thing I would like to talk about is this question we keep getting, that this range I get is not what I anticipated. And very often that comes from the term line of sight range. That means that very often the numbers given by us and other vendors, we give a number of a line of sight range. And a line of sight range is a theoretical range that you can get. For instance, if you have a very clear open area between two very tall, high antenna placed at high locations. And it also is, this line of sight is also based that there are no other RF noise in the area. So through this line of sight range that and we see vendors are trying to overbid each other by telling this fantastic line of sight range. Some have 50 kilometers, some have 60 kilometers, but it's really not, as we will show later, a realistic target of what you can expect from in a real environment. So this line of sight is often something which gives the customer unrealistic high expectation of range. However, if one vendor starts to give a realistic range while the others keep stating line of sight, the realistic one will look bad on the datasheet, but maybe be more honest. We try to, in our communication, we try to give more than one range measurements. We want to give both the line of sight because we need to compare, but we want to give the customer a more realistic expectation. So why can't we get this line of sight range in real life? First of all, you have obstacles that are shadowing, so that there is no clear radio path. You get reflections, you get diffractions through different objects. And you have something called ground fading. That means that the ground itself takes a lot of the energy away from the signal. And you also have background noise. So these are all factors which will decrease your range drastically compared to this ideal range. So here I will try not to be a bit light on the theoretical part, because there's a lot of papers and theoretical studies I can go into regarding range, but that was not my intention in this webinar. What we want to show here is basically what we call a link budget. That means what are the numbers which affect the link budget, or what he would call it, the path loss. And the path loss will give you, the more path loss you can accept, the longer your range will be. So here we see this range is will be given by the output power at the transmitter, PT. It will be given by the gain of the transmitter, the gain of the antenna of the receiver. So the gain is referring to the antenna gain here, the sensitivity of the receiver, and the noise level, external noise level at the receiver end. So this is just showing the different factors, and we will then discuss how you as a product owner or a system owner can affect these different things to increase your range. This graph is trying to show the same thing in a more visual way. So the intention of this graph is on the left side, you will see the signal strength through this triangle. So by moving the triangle up and down, up, if you have a more signal strength at your transmitter, and if you have lower signal strength from your transmitter, this will go down. The three diagonal dashed line are showing the loss as a function of distance. And as you see, the sensitivity level is the black line at the bottom. And you see that in an open outdoor environment where you have line of sight, you see the signal can go very far, above 10,000 meters in this case. If you then go to an urban outdoor with a lot of buildings, trees, stuff like that, you will see that the signal, propagation loss is much more steep, and you will get a much shorter range. And in an indoor environment, it's even worse. And then you also see how the noise here affects the range, so that if the noise will be kind of on top of the sensitivity level, which means that the range will hit this noise level first, and thereby reduce the range. So from a visual point of view, we see that we can increase the range by moving to a better environment outdoor. You cannot, of course, change that in real life, but principle, you can do that. You can increase the signal strength by having this triangle on your left side move up. You can increase the range by having the sensitivity level go down, meaning a more sensitive a radio with better sensitivity, or you can reduce your noise, and that will also affect the range. Now, this is not something you can change in real life. What you can change is, or what factors affect range are then these, which I will go more into detail of each of them. It's the output power, it's the antenna choice, it's the environment that you operate in, it's the sensitivity, it's the frequency you operate on, and it's the noise in your environment. So here I will just have this same equation at the top, but just highlighting the point that I'm discussing now. So the output power is one way to increase the range. It has some drawbacks. First of all, the more output power you have, the more battery or the more current you use, and the worse it is for battery lifetime. So it's not a free thing to do, but you can increase the output power. Also, you have to be aware of regulations, because in different frequency band there are different regulations. So that means you cannot simply increase the output power as much as you want to, due to limitations in the regulations. For instance, in Europe, in 868, it's limited to, for most of the band, it's limited to 25 milliwatt, and if you go to some other bands in 869 megahertz, for instance, you're allowed to send 500 milliwatts, which is significantly more. Antenna choice is to some degree the same as the output power, because it will affect the radiated output power at the transmitter end. That means that you cannot, at the transmitter end, you cannot just increase the antenna gain because there are regulations. However, you can, so you cannot really extend your range, but you can lose range by having a poor antenna design. That means that if you focusing on product design and having a hidden small antenna inside the product, that means that you may be having less radiated output power, and that will reduce your range compared to an external antenna, for instance, which are not that sexy from a design point of view, but gives you a better range. In the same matter as antenna choice, we also have the antenna position, which is a more critical thing that you can play with, because the antenna position will also affect the range. And as we discussed earlier, open areas and open fields are the best. So in case you're monitoring something deep inside a big machine, maybe it is good to actually have an antenna cable and an external antenna for that specific case. We also see these electricity meters, which are inside metal cabinet. Not a good position for an antenna either. So if you can have a small antenna cable and put the antenna on the outside of that metal chamber, you will significantly increase your range. But this also has to do with, this is a trade-off versus like installation cost and also design. So you have to look at your product and consider what is the most important thing for you. Receiver sensitivity, yes. So receiver sensitivity is obviously is how well your device can listen and how weak signal you can receive. And for the receiver sensitivity is of course very good to have the better receiver sensitivity is, the longer your range can be. How you can affect the receiver sensitivity is normally by using the latest chips and modules, of course, which are normally better than the old one, and also you can affect it by changing the data rate. So that means I will look at the case study later. We have compared 5 kilobit radio versus 50 kilobit radio, and that will give you 5 kilobit give you significantly longer range, but it will give you typically 10 times the current consumption as well, because your transmission will take 10 times longer. And we also see some radio system like LPWAN going down to 100 bit per second, and they also can go lower than that, and that will also increase the range even further, but at the cost of even much higher current consumption. So there are no free lunches here. It's always a compromise between different elements. Noise is not something which is emphasized a lot in the product specs you will find there, because it's not really related to any product. This is how the world is, but it is something in a real life that you must take into account. So what we show here at this slide is a noise scanning, or we were scanning a channel for noise, and we're doing it first where we have it shielded, so there is no antenna on the device, so it's not picking up any noise from the environment, so there's no external noise. We see the noise level is about slightly below minus 120 dBm. Then we have the same measurements from some field tests we did. It's in the Oslo area, but it's an outskirt of the city. So it's there we see the noise level go up to like minus 115 dBm. And then we've done some measurements in our office, and where we have a lot of equipment, of course, and it's in the middle of the city. And we see noise level is significantly higher. We also see that it's more bursty of nature. That means it has higher variation. This noise that we see here, which we have measured in the office in Oslo, comes from different things. It comes from LTE base stations. It comes from all electronic equipment like PCs, monitor, other stuff we have in the building. It comes from other wireless network in the area. We know there is a AMR network in Oslo with 700,000 devices operating in this frequency band, so that can be it. So there are a lot of things, radio systems and noise sources that creates this background noise. One thing to note here is that because the noise is some time varying, that means that elements like having short packets can be a very advantage, because you can actually hit these small periods of low noise. So if you have small packets and combine that with retransmission, for instance, you might get the practical same range as you will get with very long packets. If you look at the right side, the noise spectrum, between 8 and 9 seconds, you see the noise is varying very much. And if we were doing LPWAN, like LoRaWAN or Sigfox and these kind of things, the packet lengths are more than 1 second. So that means that you will have a long packet will for certainly get many of these noise spikes in it, while a short packet at some couple of milliseconds or 10 milliseconds could hit these low noise time slots. So this element I talked about when you reduce the range, you reduce the data rate and increase the range, that is very true for a theoretical environment, a theoretical no noise environment, but in practice you don't get that same effect. Frequency. So what we have seen is that these different factors affecting the propagation loss, but the relationship between the propagation loss or the path loss and the actual distance is very much a function of frequency. So that means that when you double your operation frequency, it will give you basically 6 dB loss, and that equals half the range. So that means, so that's the kind of easy rule of thumb is double the frequency, half the range. So this is also why 2.4 GHz is not that suited for long-range communication. We do see a lot of long-range communication at 868, but we also see it at 169, which is used in Europe. There are other low-frequency bands also possible in other parts of the world, but 169 in Europe is very popular simply because it gives 5 times the range of 868 MHz. Lowering the frequency is not free of charge that either, because it's a trade-off as well, and the trade-off here is antenna size again. So if you want to make a very small product with a embedded antenna inside the product, this 169 MHz will not be very easy to do at that type of product. Also, when you talked about how this path loss converges to meters, you have to think about this free space, and the energy between two antennas is not a thin line, but it doesn't go as a line, thin line between these two antennas. It is actually a large area here between them. So that means that if you are standing on the ground and you can look at a transmitter 100 meters away, or you do not have line of sight because of the ground. So you do have line of sight because you can see between them, but you do not, in terms of the perfect RF connections, you have to put this antenna up into 100-meter tall towers. Then you will have a perfect connection, and that is this theoretical connection. So it's not about it's all about finding, when you place your devices, get as much open space between them as possible is the basic idea. However, we know that this is not really practical in a real life scenario. I just also wanted to comment that you are free to post any questions in the chat window if you want to. I forgot to say that in the beginning, so I apologize for that. So if you have any questions, please post them in the chat window, and we will answer them at the end. Yeah, I wanted to show this figure again because, again, I wanted to summarize that finding an open area is the best. Increasing the signal strength will be good. Better sensitivity is good. Reducing noise is good. So basically, this all, again, summarize all these factors that we can influence. This is a very dangerous slide because it might give you unexpected or unrealistic expectations again. However, this is some estimations based on an 868 MHz radio. So at 169, it would be much better numbers, for instance. It would be 5 times the range on all these numbers. Here you see different path laws at your left. And we see this 124 and 134 are the ones we get in our RIIoT product, which we will show you some results from afterwards. And 150 might be the results you get from LPWAN solutions. And first I have this Lineofsight range, which is a theoretical range based on what is known as the freeze equation. And this, again, shows fantastic range. We have this LPWAN could be 850,000 or 850 kilometers. And we could have like 44 or 138 kilometers in different modes. We do see some examples of measurements that are close to this. For instance, if you put the receiver in like a balloon and let it up in the air, because then you will get zero noise up at this balloon. If it's 2,000 meters up in the air, it will practically zero noise up there. Man-made noise from Bluetooth phones and LTE base stations and these kind of things. And in addition, it will be a fantastic line of sight between the transmitter at the ground. So we have seen somebody reporting 700 kilometers, but again, the use case is very strange, communicating to a balloon straight above you. If you look at a real overground test with antennas just placed 2 meters above ground, you see that, and communicating over a completely flat surface, that you will get like 1/10 of this range, which is a typical rule of thumb. Again, this is a noise-free theoretical thing. If you add noise, and here I think I added 6 dB noise, which is not what we have in our office, but what we have in just outside of Oslo. And there you see the range is starting to be even half of the above mentioned. Then we have an urban area range, which means that we no longer have line of sight, but we have one antenna placed like 50 meters above ground, and the other is more on ground level in the city. Then you see that you could get maybe 3,000 in a very good radio, and maybe 1,200 meters or 600 meters with other radio systems. Indoor is definitely the most challenging part to estimate, because what is the floor made of? How does the environment look like? Again, these are more rule of thumb type of numbers based on actual measurements we have done in our building. So it's not really something which is universal, can be applied universally. Yeah, link margin is also one thing, but you have to take into consideration when you go into a urban environment or into indoor environment. And that is the fact that because the environment is changing, the signal strength will vary between different packets. So that if you send one radio packet and 10 seconds later send a new one, it might come to the receiver with a completely different signal strength. And when we're doing outdoor test in Oslo here with our radio systems, we saw that, okay, when we had a person going with a device on the street, every time a bus drive by, we saw the signal level drop significantly. So this is how the world is in an indoor environment. People are moving, doors are being opened and closed. So the environment is never static. So that means when you set up a link, you need to make sure that you're not just at the edge of where you can operate. Also, the noise level, as we saw above, is very much time varying. So that means that the noise level it can vary over a day, or it can vary from second to second actually. So that means when you set up a real link, you have to consider these elements and actually choose a low range that you maximum can have. So just to summarize the tips and tricks, yeah, how to increase RF range, you have to make sure to be on the as much output power as you're allowed to, and possibly also the directive antenna. You have to think about antenna placement, high up, where it's free, so not inside cabinets and stuff like that. Foggy weather rain, you cannot really change. Also the base station you cannot really change, but you have to be aware of it, where are the cellular base stations in the area, the LTE base stations. What you can trade is data rate for range, and you can of course move these antennas around again. And you can of course also reduce your operating frequency. So now I just wanted to round up by summarizing on some of the measurements that we have done on our new RIOT platform, which is now operating at 868 megahertz. It is based on IEEE 802.15.4, and we are operating at two different RF rates. We have 50 kilobit per second and 5 kilobit per second. So we have been out doing some range measurement in an open area to get some feeling about that. We then went outside of Oslo, in the outskirts of Oslo, I should say, and found two places where we can actually see each other. It's not a perfect line of sight because we had the ground pretty close to us, but at least we can see between the two different sites. And we got a very good link, or a stable link, I should say, at 7.6 kilometer, I think it says here. I think it's difficult to read the actual readout. So yeah, if you are able to put the antennas at high locations and get a good line of sight, this is the range you can possibly get at the. But we also did measurements inside from our office, where we had one device in our offices. So it wasn't. We could have placed the antenna up on the roof on the tall, but we didn't. So we could have increased this range slightly. Here we see that we measured, if in the left down corner, you see we measured receiving packets well at 580 meters, where we received them at minus 100 dBm. The sensitivity at this radio is actually minus 120. So in a noise-free environment, we should be able to receive them down to minus 120 dBm. But basically, this tests stopped around 100 dBm, and that is due to the background noise that we see in the office, and the LTE base station that we have on the building next door is one of the key factors in our evaluation of that. So we see again something like 500, 300, 300 and 400 meters here. We received good links on different locations. So yeah, this fits with the above mentioned theoretical calculations showing 1200 meters. The reason the 1200 was based on the antenna on the top roof. And again, if it hasn't been for all the noise in the city, we could have reached much further. But I mean, noise is there. All the laptops and the cellular phones and the LTE base stations are there, so we cannot change them. So this is the realistic number you will get out. Yeah, this was again just explaining why we didn't, explaining what background noise we had at these measurements. Here you also see the noise level going up to above minus 100, so the noise level peaking at like minus 90 here or something. So at that noise peaks, these packets at minus 100 dBm would not be possible to receive. So the reason we have received them still and had at that position zero packet loss is because of the acknowledgement and the retransmission in the protocol, which ensures that even though we lose one packet, we retransmit and get the next one through. And with this noise pattern that we see in a real world, that feature is very important. While other radio technologies, which are basically shoot and forget, that you don't really confirm that you get the packet through, which is typically of Sigfox and LoRa, you are more depending on being lucky, I guess. So, summary. The line of sight range, which we and others give, is a very, like for instance, for this RIIoT 5 kilobit, we had 138,000 meter. It's a very nice number, but it's not really practical. It's because the physical world is there. There are objects in your path. There are background noise. You cannot change that. You cannot ask the mobile company to turn off their cellular towers. That is it's not possible. What you can change is the antenna gain and position. That's a trade-off versus design and installation cost, I would say. Having a big antenna, external antenna, is not that sexy. You can trade versus sensitivity. That will affect your data rate and thereby the current consumption. And also you have to be careful if that means going to a very low data rate means that you skip retransmission. It's not sure that you will get the actual benefit in a real world anyway. You can change your operating frequency. Going down is better. Also, it is significantly better just in open space, but when you go to penetration in building, it's even more important. Again, this is a trade-off versus antenna size. And also the output power is something you can increase, but you need to watch regulations, and it has the cost of current consumption again. And also a very important note is there are no very good or very accurate prediction model. We have customers coming to me saying, I have this building, it's 10 floors, I have one device in the basement, I have one device in the 5th floor. Which radio technology can work? Can this radio technology work? And this is, of course, a question which is impossible to answer in a very accurate way. It is important that you test the solution in the real environment where you can play with the factors above to try to maximize it, and basically test if you get a good solution or not. Okay, did we have the? Is there chat window? Yes, I'm now looking at the questions. What equipment do you use? Basically, we use a development kit for a chip here, or we have also used the spectrum analyzer, which is a more expensive way to do it. But there are some development kits on this radio chip which have software, and so basically it listens to the different to a certain channel and samples the background noise. Yeah, rain and fog will influence the. Of course, it's hard to say how much. Again, how much is it raining? Is it raining lightly or heavily? Again, I think that at 2.4 gigahertz it's worse, because 2.4 gigahertz and water goes very poorly together. So again, going into lower frequency, it will have less effect, but it's hard to say an exact number. Yes, Thomas is asking about frequency range of the plot. I was assuming you mentioned this plot showing the path loss versus distance, and yeah, this is the plot is more a principle than it is accurate, showing the different principles, and it's not really the plot is not really given to a specific frequency range. This. Yeah, so simulation tools. There are some simulation tools online. I know that there is one prediction model or like a tool out from a company called Texas Instruments, which I guess you can try to Google that. I think it's called range estimation for indoor and outdoor, they call it, which is but again, it's just there are no really good prediction model for indoor and urban area. For open site, it's the prediction models are there, but for indoor and outdoor, it's not that easy. The noise plot was made at 868 megahertz. I do think the noise at 169 is slightly lower. I do think that the noise we see at 868 is a lot influenced by these LTE base station around. When we're operating at 868, we do see the influence of base stations operating at, I think it's 890 megahertz or 900 megahertz. So that is again very much a threat for the 868 megahertz band, again giving the advantage of 169. However, we see a lot of deployment in 868 megahertz range, so it's still possible. If we have we don't have a development kit at the moment which allows you to have these noise measurements. But that's something I can take back to the team so we can discuss if we want to make that available for the end user. Frequency hopping is a question from Stefan. Frequency hopping in itself doesn't affect range. However, you do get an advantage versus noise or variation, say noise and fading, because the fading, the variation of the signal over time will give you it will be different for different frequencies. So if you're sending the same message on different frequencies, so that means you have retransmission at different frequencies, you will for certainly get a more reliable link on the range, which is more lossy with the single channel. So you don't increase the maximum range, but you can get a more reliable channel for the range. So you need less link margin then. I think I answered all the questions now. Yeah, we do apologize for the timing in the US. We understand it's not possible to. The timing is not good for that, but we do record these so that anybody can listen to these webinars later at a more appropriate time. So I would like to thank you all for listening in, and please also check our website for more information also about the RIIoT, and also there will be a new application note on range going more in depth. That will be out shortly. So you will get, it's not out today, so you won't find it today, but it will be out in a couple of days. So you can get more details there if you want to share it with some colleagues. So thank you very much for your attention, and I wish you a good day for the people in Europe, and I guess a good night for the people in the US. Thank you very much.